Today we're going to have Ruth Richardson and Monroe Weber-Shirk. Both are from Civil and Environmental Engineering. They're down in Hollister Hall. And last week we had these really crude cartoons of water and wastewater infrastructure. And I don't know exactly what they're going to talk about, but I bet they're going to cover those things in more exciting detail than what was on that cartoon that I gave you. Monroe is going to talk a bit about AguaClara, it looks like. And I'll let him say what that is, but it was something that I did when I was in grad school. It was a great program. It's only getting bigger and better as time goes on. And Ruth was my advisor. So I'll just leave it at that, and I'll let them introduce themselves and talk about whatever they're going to talk about.
Thanks, Brian. So I suppose I'm supposed to be right here all the time, right?
You don't have to. Just don't worry about the video.
Hey, so good to be here. Fun to talk about water. In preparing for this, it's completely unclear what I should talk about. So I thought I'd give a couple topics, and I want to give you a chance to say what you actually wanted me to talk about, and we'll see whether we can make that work with the slides that I have. So no matter what you wanted to talk about today, I'm going to talk about water. Okay, so we're at least narrow down that far. So where do you get your water that you drink?
They should all know this.
6 Mile Creek.
6 Mile Creek? Anyone else?
Hugo Lake.
Hugo Lake? And it's great. I don't, nobody drinks bottled water? I mean, on the way up, I passed Chemung Springs truck, and I was a little bit annoyed about that. And I also
actually from Chemung Springs.
I'm sorry. And then I also saw the Bolton Point water truck going by. They're probably on some service call somewhere. They're the folks that are taking water from Hugo Lake and treating it for us. So anyway, yeah, we get water from these various sources, and you want to think about where are people on the planet getting their water from, and what might they really want. I'm a salesperson for the benefits of safe water on tap. So we have this amazing thing where you can, while you're taking the shower, you can drink that water and it is perfectly fine. A matter of fact, I'll go the whole way. The water that's in the tank of the toilet, the part that's up against the wall, that part of the tank of the toilet, okay? You can dip water out of there and drink, and it'd be perfectly fine, okay? The next part, not so much, but that stage is still perfectly good. And when you wash your dishes with water that you can drink before you stick the dirty dishes in, I suppose. And I think that's pretty cool. And I think about the many people on this planet who don't have safe water coming out of their taps, or don't have a supply of safe water for access for use in their households. And think about, how many of you have taken some version of microbiology? Okay, a whole bunch of you, okay? So think about, as a microbiologist, if you had a family in a household where the water coming into the house is laden with pathogens, how do you manage that household so that your kids stay healthy? And if you think about that for just a few minutes, you realize this is a nightmare. Trying to figure out how do you, the carrots that you bought at the market and you'd like to wash them for your kids. Oops, how do you do that? And there are ways to do it, but it is a major challenge to keep your family healthy when the water coming into your house is also laden with pathogens. So I get excited about this. I think it matters. Another topic that is of interest is metering. There's not enough water on the planet to give everybody all the water that they possibly want. In this part of the world, water is metered, meaning that I pay for the water that I use. And that hopefully gives me a little bit of incentive to not waste water. There are many parts of the world where people are connected to some sort of a water supply system, but they're not metered. And the reason that they're not metered is, one, the meters are expensive. The meters can end up being one of the more expensive parts of the infrastructure. So the cost of meters is one problem. And the other problem is that meters have been associated with privatization. And so meters have a bad name. And so people are afraid of what's going to happen if their water is metered. as part of AguaClara, we haven't officially taken a stance, and we haven't said if you're going to have an AguaClara plant, you have to use meters. And none of our facilities, meters are not being used in a widespread way at any of our facilities. But from a standpoint of this would be the right thing to do, I'm pro meters. I think people need to be billed based on what they use, so that they have an incentive to fix a leak in their toilet that's causing, enough water for 10 people per day just going down that one toilet. So I think meters are a good idea. Another idea here is, I'm talking about the goal of having one pipe coming in, meaning all the water that you use in your house, whether you're using it to wash dishes, flush your toilet, or drink, I'd like all of that water to come into the house safe and not laden with pathogens. And then I'm going to turn over to Ruth the issue of, then there are these several streams of water that leave your house, and how should they be leaving the house and how should they be handled? I've taken the easy part of the job, and I'll let Ruth handle the more difficult one. In dealing with water or dealing with infrastructure, one of the goals is to do something that is resilient. Create a system, an infrastructure that if something goes wrong, it will be fixed because the incentives are there to get it fixed, and people have the capacity to fix it. That's a really simple concept that a lot of infrastructure hasn't had, especially in the developing world. This notion of building things so that it will be easy to fix it and maintain it over the long term. And I get excited about human-centered design. It's very easy for engineers to design things and forget that ultimately it's going to be run by a human. There's going to be a human that's going to be responsible for maintaining that facility. And think about how does that human interact with the facility, because that interaction is key. If that interaction is awkward and difficult, the system won't actually perform as well because the person who's running it won't engage as well with it. And there are some very key things that we do to design our systems so that it's easy for the operator to run the system. Okay, disruptive technologies. That's what we're doing, creating disruptive technologies. Enough about that. The question I have is, what do you want to talk about? Why did you come here today? Do you want to spend like a minute talking to the person next to you and then tell me what you came up with, what you wanted to talk about today? Talk. Get noisy.
Asked this one last time.
Yeah.
You just say what you said last week. Well, maybe last week changed what they wanted to come here.
How about as soon as you and your team have an idea of something that you want to talk about, write it on the board. That way I don't have to remember it. Good. One brave soul.
I'm totally stealing your idea, I think.
Make sure we at least have something for Ruth to talk about.
What word is it going to talk?
Can you write on the other side of the board? Sorry. The video doesn't cover this part of the board.
Excellent.
okay with you, Monroe, too, I'll just to say to everybody, if you ever have a question or you want to stop and talk about something, feel free. Definitely speak up in the class.
Definitely.
And we'll have some time at the end for discussion as well.
Water efficient technologies. Does anybody else wants to write something up here? Or say something because you didn't want to write it down? So we have gray water reuse, disruptive technology, green infrastructure, water efficient technology, and appliances. Excellent.
I think we can add basic water access and quality.
Okay, so water access and quality.
Or also just like some of the cheap technology solutions that AguaClara.
We would never use the word cheap.
Innovative.
Oh, I would. Yeah.
Yes.
So I'm interested in the economics of all this because I mean, if you value it, depending on how much money you're willing to pay for it, somebody that's like the metering, which we could use up here, California should be willing to pay for our metering so they can have water. To me, it's like the economics of it and the valuing of it is kind of at the core of this.
So how do you spell valuing? Or is there a red line underneath that?
VALUING, I guess.
Thank you. Okay, so this is what we're going to do. First, I want to give you this little pitch. I'm going to try this on you. So, Tegucigalpa is a major city it's the capital city of Honduras. I don't know, there's 1 million people living there. And they use a reasonably high-tech, designed in Europe, water treatment plant to serve the city. And when I go to Tegucigalpa, I don't drink the water from the tap because I don't consider it safe. Okay? There are now walls. I'm feeling restricted here. When I go to Tamara, which is a town 20 minutes or 40 minutes north of the city, that's served by an AguaClara facility, I drink the water from the tap in that town because that water is safe. And I forgot my next line. Okay. Oh, and that plant was designed by Cornell students. People from Tegucigalpa are actually moving to Tamara because the water is better in Tamara than it is in Tegus. And if we can provide safe drinking water to a small town called Tamara with 3,500 people in Honduras, where the government is quasi-dysfunctional and poverty is rampant, my statement is we can do it anywhere. Maybe not quite anywhere, but almost anywhere. Okay, and then our success is based on an innovation system. That includes students at Cornell, it includes faculty, it includes professional engineers, it includes partner organizations, and it includes communities. And I'll show you a graphic kind of illustrating how they all connect to make this happen. And so by connecting all these players together, we're transforming this problem of pathogens coming into our houses in water into a solution that works and that is resilient and that is low cost and is high performing and that people are willing to pay for mostly. Okay, so this was just a drawing of the plant that's serving Tegucigalpa. So, and what they don't show you here is that there's nice computer panels controlling the system. So it should be like, it's like cool, right? It's got computers that control it. It's technology that must come out of France. And this technology is still being built today. So that's a system that isn't producing great quality water. And here's a plant that is producing high quality water. And this one was built in 2007 or 8. And what makes it produce really great water is hiding over there on the side is our latest technology, which is a filtration system. What's interesting is the technologies that are inside this are not so different from the technologies that are inside this system. At the core, the physics and the chemistry are very, very similar. But how we've designed these facilities is completely different. And how we think about our operators and how we run these systems is completely different. And how much energy we use to create the water is to clean the water is completely different. So how is this working? So this is, this image of there are Cornell students who are working in the labs, conducting research. We're working on creating new theories about how, for example, how flocculation works. Students are working in the labs to create the designs for these facilities that are being built. The facilities are being built, and ultimately people get to drink clean water. And I've color-coded this with, up here is red. This is Cornell red, okay? And down here blue is kind of on the implementation side. And you can think about this as, this is journey inward, and below is journey, outward. And those two have to talk to each other. This, what's happening in the field, feeds what goes on in our labs, and what's going on in our labs ends up changing what gets built in the field. Let's make this one step more complicated. So this is about the network that's happening. So here I am at Cornell. I'm the only person that got my name on here. That's because I made a slide, I suppose. So I'm directing teams of students who are doing research on all different kinds of things, doing design work. Okay, so they're all in Cornell red, all right? And then out in the world, there's a network of partner organizations. So there's a partner who actually builds a facility. There may be a contractor. There's skilled laborers who end up building the system, building the infrastructure. There's the regulatory agency of the government of Honduras that we need to be talking to. There's funders, for example, the Swiss government who's funding some of these plants. So they are all part of this network that the implementation partner has to engage. And out here, okay, so my implementation partners are blue, and there's some redheads out there because there's infiltration by former Cornell students into this system. All right, and then one level down or one level further across, we come to the community. Okay, so wait, so here's Cornell. This could be happening in Honduras, one region on the planet. And then within Honduras, one community is ultimately getting this infrastructure. They live in houses, there's people there, and they get clean water coming out of their tap. And there are these places where there's interface between these different groups. So for example, the implementation partner has to talk to the water board who ends up running this facility, because you need to have governance involved in order to make this all work. And what we're missing is this big circle. This is going to be part of my pitch to Ken Fox in a couple days. So what we're missing is this piece that connects what's happening at Cornell with what's happening out there in the world. This is this international connection where there needs to be another director working with me who's focused on the journey outward piece. So I'm focused on, my real passion is about the journey inward to research. I'm passionate about the journey outward too, but I want someone to help me with their focus being the journey outward and sending engineers out and working with folks in the field, providing these really smart people who work with the partners to get these plants built. So again, emphasizing that there has to be a connection between what's happening in the field, the journey outward, and what's happening in our labs. So just an idea of what kinds of activities are going on. So here there's laboratory experiments, one of many things. Here there's a focus of technology transfer or knowledge transfer or capacity building. Here the focus is on implementation, and then ultimately the goal is to produce a healthy life, a better world. We're thinking about who's involved in these different activities. Here it's Cornell faculty and students. Here are AguaClara professionals. Here are local professionals, and then here are community members. So the different kind of roles that we see at these different levels. Ah, yes, and of course there should be Cornell students who go the whole way into the community and do research. Okay, that was one community. What we really want is to have impact, so you want to be dealing with multiple communities. So one partner will work with multiple communities. Right now, the 9th plant in Honduras is being built, so that's a sense of what's happening in Honduras with one partner working with many communities. You can take this up one level further, and you can say, but we're not only working in Honduras, we could also be working in India. We are working in India. We could also be working in other countries. So you end up replicating that. So now we're working in multiple places on the planet. And if you want to really blow your mind, you can say, well, you can take this whole thing and rotate it around Cornell. What does that mean? If I rotate this whole system around Cornell, now I'm not just working on solving the water problem, but other faculty are working on solving other problems, like energy or like wastewater. Okay, so this entire model can be replicated as well. Anybody want to ask any questions about that?
Do you have other faculty who are actually buying into? I mean, I love the vision you have. Do you have other faculty buying into those other pieces?
I don't have faculty buying into pieces beyond the wastewater side. Like, but getting somebody involved in energy, I could. Give us time. Okay, just a little sense of how big this problem is. Wait, we only have like 10 minutes left. So my point here was that there's a whole lot of people. Like you can come up with these crazy numbers of, we need like 3.5 million liters per second. This liters per second, okay, you consume about 3 milliliters per second of water.
There's some buckets there.
There's the bucket, okay? 3 milliliters per second. You can like, okay, use a little chunk of water per second. That's, if I'm designing a facility for you, I need to have a plant that can produce 3 milliliters per second for you. Multiply by the number of people that I have, and that's how many liters per second of water I need. And if you do it on the planetary basis, based on the notion that there's about 3 billion people that don't have safe drinking water, and yeah, I know those statistics don't line up with anybody else's, but that's based on experience and guessing. There's a lot more people out there that don't have safe water than what most people acknowledge. So that comes up with this 3.5 million liters per second of unmet demand. There's population growth, and there's transition from rural areas into more urban areas at the rate of about at a rate of about 70 million people per year in the global south, which translates into this much additional need, even just in rural areas, for safe drinking water. And then here's our measly little, what AguaClara is doing. It's like we're not even on the charts yet, at 110 liters per second of installed capacity. So there's a whole lot of work to be done. There we are in Honduras with 8 facilities serving 7 communities, and the 9th facility presumably coming online like this week. So we'll get our first data out of that plant this week. So since the fall of 2012, okay, so we're working in Honduras. We've got great connections in Mexico, nothing on the ground in Mexico, but connections. And we have a person on the ground in India working at the village level in India. I want to show you just some pictures from Honduras to give you a sense of what happens for the construction of these facilities. This one is being built for a town of 6,500 people, so a nice sized town. Their water source is water coming out of a side of a mountain that's about 15 kilometers away, and their water is always a little bit turbid and quite turbid sometimes. So they need water treatment. Their water quality is terrible. And so this plant is being built for them. And this facility was designed by Cornell students. The core technology was designed by Cornell students. The structure was designed by a civil engineer in Honduras, a Honduran, and the architecture was designed by an architect in Honduras. So there it is, and there it is as of a few days ago. And what I'd like to do is now go inside that building for a little bit, just show you what the technologies are. So we need these technologies. We need to be able to measure flow rates, dose chemicals, get particles to stick together and grow in size so that we can settle them out. We have a technology we call a flock blanket. It's a fluidized bed, an upflow fluidized bed of flocks, dirt particles that act as a filter. We use plate settlers. We have a filtration technology, and we disinfect. Some of these technologies have been around forever. Some of them are brand new. Like this one is an AguaClara invention from 2010. Dosing chemicals using gravity and not using electricity not using pumps is a technology that we developed. We started working on this in 2004, and we have a really cool technology now to do that. Okay, so inside the building. So this is that facility that will serve water to 6,500 people. The tanks that we're looking at in the foreground are sedimentation tanks. These are the plate settlers. The plate settlers, wait a second, I should start at the other end of the plant. Let's go back here. So this is the entrance tank where the water comes in. That's why it's higher than the rest of the plant. It's where it starts. And then there's a flocculator and then sedimentation tanks. And back here there's filters. So that's the order of flow through the plant. Entrance tank, flocculators, sedimentation, filters. And I thought we should do a dance. Okay, so water we'll get there. Okay, so first, this is our flow measurement device. It's really simple, and it ends up creating a linear flow meter that the height of the water in this tank directly relates to the flows through the plant. They just put some labels on the side of that, and they've got flow measurement. What's not shown yet is there's going to be our dose controller, which is a whole other really cool technology that I could spend several days talking about. Here's the flocculator, and the point of the flocculator is that before this, you've added a chemical, an aluminum-based chemical that is sticky, and I'm going to just stick with that notion. It's sticky, okay? And it sticks to everything in the water. So it's a glue that has adhesive properties underwater, which most glues don't, okay? So you add this adhesive to the water, it precipitates, and it sticks to everything that's in the water, including all the particles that are in the water, and it then makes them sticky. So that when those particles hit each other, they stick together and agglomerate and become like snowflakes, which the reason that snowflakes grow large is because they're also sticky, especially if the temperature is close to freezing and not real cold, which is why you get bigger flakes when it's close to freezing than you do when it's really cold, because the snow is stickier when it's close to freezing, all right? So you can get big flocks, that's what these are called. So what we need to do in the flocculator is we need to get particles to collide so they can stick together. And the way that we do that is we send water through this channel that does this. So the water's going up and down, up and down, up and down about 60 times. And as it's changing direction, it's causing turbulence, and that turbulence is causing particles to collide. Okay, then the water goes to sedimentation tanks, and here they are, they're assembling some pieces in the bottom of the sedimentation tank. And there they're putting the plate settlers in. Let me just describe plate settlers. So you have plate settlers where the water is flowing up between these plates. And as the particles are traveling between these plates, they're under the influence of gravity. So as a particle is traveling with the water between those plates, gravity is pulling it down, which means that there's a very good chance it's going to make it down to the lower plate. So it's slowly dropping because of gravity, ends up falling on that lower plate, and then eventually it will avalanche down that lower plate and return down into the bottom of the sedimentation tank. So out of the top of these plate settlers comes relatively clean water. Okay. And then there's a filter. And then we add chlorine using our dose controller.
Excuse me, could you just comment on how long, what's the lifetime of that? Like how long does it take to build up the material at the bottom? Does it have to be cleaned? How do they be, what's the maintenance for that stuff building up on the bottom that won't down the leaks?
Okay, so the maintenance for the sludge, the particles that end up in the bottom? Okay, so at Cornell Water Treatment Plant, in their sedimentation tank, they turn off a sedimentation tank. They have two. They turn one off, and they actually go in there with, I think, with fire hoses and blast out the sludge like every 6 months. In this design, we're currently having to open up valves to drain a little bit of sludge out on a daily basis, and then every couple weeks drain the sedimentation tank and clean the very bottom of the sedimentation tank. And it's probably about a 20 minutes of work, and then about maybe another 20 minutes to get it back online. And we can take one sedimentation tank down at a time. One of the cool things that happens in the bottom of this tank, which I didn't talk about, is there's a flock blanket. It's a fluidized bed of these flocks. Think of snowflakes in water that provide additional places for the particles that you're trying to remove to stick to those flocks and hence become larger and be removed. And that flock blanket, if you just start with a brand new tank, it depends on the raw water turbidity. It takes from hours to maybe 2 days for that flock blanket to grow. While that flock blanket is growing, the water quality is still pretty good, but it gets a little bit better once that flock blanket is in place. Did I answer your question?
Yes.
Okay. My goal is to design a sedimentation tank where they never have to take it offline. So now, right now we're at like a 2-week take it offline. I want to get that to you don't have to take it offline. And it's a matter of of designing the geometry of the bottom of the said tank, right? We're getting closer. Anybody else want to jump in with a question? I wanted to acknowledge that I asked you this question. So I'm going to leave this one for Ruth. Low cost. So these technologies cost significantly less than conventional designs. They don't use any electricity, so right away one of your operating costs completely goes away. And they require less labor. This is the irony. They require less labor because one person can run this whole facility. With the way the world has gone with making sophisticated, modern, advanced technology, that means that they're going to use the electronics and computers to control things. And the levels of systems that you need in order to control a facility when you go to computer control. So there's the computer hardware, there's the software on that computer that's specialized, there's an interface between that computer and some control system out in the real world, there's the actual electronic switches that turn things on and off. Often there are then air valves that are turned on and off that then finally control water valves. So you have all these levels of mechanical and electronic systems, and failure in any one of those brings your plant down, and you require experts with different specializations to be able to repair and maintain those components. So what was meant to be a labor-saving device so that one person could operate the plant actually ended up making it so that one person can't operate the plant because they need to be able to call on specialists to maintain all those systems. Here we go the complete other way. We make a system that we use fluids. We use really smart fluids, very simple controls using fluids to run these facilities. So now one person can truly run the whole system, and if something does fail, they can repair it. So it went smart and beautiful and simple all at the same time.
Excuse me.
Yeah.
What about the cost of the chemicals to treat the aluminum, and where is that sourced from?
So these coagulants are a global commodity. You can get them anywhere. The irony, when we go to India, they say, can you get the chemicals here? And we say, yes, we know we can, because the chemicals that we buy in Honduras come from India. So it's a global world, and you could buy, these almost, I don't know if every, but almost every country has conventional water treatment somewhere in that country, and so they're using these aluminum coagulants as part of that. The costs are really, really tiny. The cost for like a kilogram of alum is something on the order of $1, and that 1 kilogram is going to treat, oh my goodness, you end up, help me out here, you end up using order 10 milligrams of that material per liter. So how much does a liter cost you? So it means it's 100,000. You treat 100,000 liters for about $1. Yeah, that makes sense. It's cheaper than your bottled water.
What's the largest size community your technology could actually provide water for?
Right now, or
or soon, based on the technology limitation.
So it turns out that making something bigger is easy. It's making it small that's hard. When you try to make it small, then economies of scale fight against you. And one of the economies of scale that gets us with this system is that you have to have a plant operator. And the salary for that plant operator begins to dominate the costs as the system gets smaller and smaller. Does that make sense? If you've got 100 people in a village, one of them is a plant operator. That's too expensive, and there's no way that's going to fly unless they're wealthy villagers. Going bigger, you just make more elements. You modularize this, and you make more and more elements. This spring I had a team of students working on, can you design a 1,000 liter per second plant, which would be, I think that's 300,000 people. How big, it's going bigger is easy. We did this, we didn't do this. Disruptive technology, this is a disruptive technology. Like, we designed it to work for poor rural communities, and then we also hit really hard on and make it work as well as the competition. So we easily produce water that's higher quality than what the big plants do in Honduras. So we easily outperform them. And we're also lower cost. And we're also simpler to operate. So at some point you say, well then why don't you just build these plants? Why are you using the French technology or the Spanish technology? It doesn't make any sense. So this is a disruptive technology. And by the way, that's a classic business approach, that you go into an underserved market, you develop a product that is needed by that underserved market, and then you scale up and you are able to outcompete the people that were providing the wealthier folks before. It's at least reasonably green, right? There's no electricity being used to run this. The chemical use is tiny. Go ahead.
I love this. It's brilliant. I'm just curious, since you were interfaced with the community, I mean, you've got them heavily engaged. First step is obviously looking at the source of the water. Let's say it's a river, a small stream up there. And it's a great opportunity to talk to them about not drying up the river, but to take a certain amount and then deal with climate change, have a buffer and downstream users. So you didn't mention that, but is there like a dialogue about how much water to extract and how to do it sustainably?
Boy, is this complicated. Yeah, so I need another expert to work with me and work with communities. A fair amount of the communities are at least reasonably aware of those issues. And one of the communities has gone out of their way to buy more of their watershed so they can control what's happening in their watershed. There are things that you can do in the watershed that make it easier for the water treatment plant. So if you have those riparian buffers along the waterways so that there's not so much direct erosion going into your streams, then the plant doesn't have to work as hard and you're going to save money on chemicals. And it's the right thing to do. Like, you would like your soil to be on the mountain, not in the ocean. This is a good engineering challenge. Like, what can you do to make these systems waste as little water as possible? Ultimately, there are some solids that come out of the plant, and water comes out with those solids. And you'd like those solids to be at as high a concentration as possible so that you're wasting as little water as possible. Anybody want to ask any more questions about economic valuing? I'll just have one comment on that. People that are served river water coming out of their taps don't like paying for it. Because they're like, God gave us this water. Like, river water, God gave us that. Why do I have to pay for it? Granted, that argument's wrong because the infrastructure to get river water out of a tap is actually quite expensive. All the piping is actually order $100 per person in the global south just to get the water piped to your house. When the water coming out of the tap is safe and clear, like it's aesthetically pleasing, then people are willing to pay for it. And the incremental cost to make it pure and safe is about $20 per person. So the infrastructure to get you the water costs you a lot more than the infrastructure to make that water safe. And that's what, somehow that idea has gone by a lot of people. That treating water is actually very cheap, especially if you do it like this. You can treat a lot of water with very little energy for very, very tiny amounts of chemicals very efficiently.
Somewhat true here too.
Oh, absolutely.
Distribution is always more expensive.
Sure, because the pipes underneath your street, like if you're going to try to replace those, it's going to cost you a lot of money. Replacing the water treatment plant is still going to be expensive, but nothing like replacing the distribution lines. So the point was that the whole system becomes more economically sustainable, as in people are willing to pay the cost that it really takes in order to maintain the system if you provide them with safe water. If Bolton Point started delivering really crappy water, people would start rioting and they would actually start withholding payment because they're like, I'm not paying for this crappy water. So the whole system becomes unsustainable when the service is poor. I think that's where I want to end. Well, unless there's another question yet, and then I'll turn it over to Ruth. Go, Ruth. Take them through gray water. No, not through gray water. That's not nice.
from Brian's talk last week and my talk this week, you would have no idea what Brian did his dissertation on. Maybe I won't tell you, but they did indirectly involve the Ithaca area wastewater treatment plant. And if we have time, I'll come back to that link in a second. No, it's not that.
I'm happy you actually watched the video.
Was that?
I'm shocked.
I did watch the video. That is how I knew it wasn't in 1105 anymore.
Right.
I had the foresight to ask. So this should power, this should work, theoretically. Were you doing it with this, Monroe, or were you advancing on your own? Oh, okay.
Oh, yeah.
That's all right. Okay, so this is like water treatment, a topic that it would take, you could go through for many days. I'm just gonna, that's okay.
It's probably installed.
Fair enough.
Technology.
So I'm going to pick up quite literally where Monroe left off. And Monroe delivers water, clean water, and believes in delivering potable water to the tap, so everything in the home is safe, really, for human consumption. But I'm going to ask you guys then, what do you do with that? What are the different things you do with that? And then think about how consumptive those uses are, how differently consumptive they are. I mean, how do they change the nature of the water that you use for them? And while we're at it, estimate how much water you use, although I think you gave that away. In milliliters per second, which I think is pretty cryptic. Gallons per day or liters per day. Anybody know how much we tend to consume in the U.S.?
100 gallons per day.
Huh?
100 to 100.
About 100 gallons a day. 50 to 100 gallons a day is a typical sort of American consumption rate. What is the sort of least consumptive, Rita, or what water use do you have that least modifies the water? What's that? Oh, that's an interesting one. I would put that on the other extreme. It goes through a whole lot of chemical changes before it comes out the other end. Except the stuff you evaporate and breathe. Agreed, pretty clean. Hand washing and showering, yeah.
Watering plants.
Watering plants, right, which sort of also directs it back into the environment directly. Right, so there are things with very low sort of consumption that don't really add a lot of contaminants to the water, and then obviously on the other extreme, right, is toilets. Toilets pretty typical, right? Unless you have some sort of hobby where you do a lot of metalworking, you have solvents and nasty things, right? A typical person, the worst thing that we do to water is combine it with our excreta. So what I want to kind of, let me see if this goes. Oh, it's going. So we're going to talk, and we already just started talking about from potable water to waste and wastewater, what we do to our water. And then I'll talk a little bit more in detail than Brian did. I still only have sketches of sort of our conventional options for treating wastewater in the United States. Then go into some of the challenges of the status quo for our treatment options and some of the lost opportunities, the way we sort of view our wastewater and handle our wastewater. And then I'll just give you a sampling of the many, many, many technologies that are out there that are alternative technologies and systems for more sustainable water and human waste management. Okay, so we kind of came up with this number, although these numbers are going to be in liters, so this is like 140,000 liters, 100 to 140,000 liters of water per year that we send, most of us, to a wastewater treatment plant. All right. Any idea on these other numbers that I've sort of blocked out? When we measured the fecal material in kilograms, urine in liters, right? And then there's two types of water here, right? There's our flush water. We have these cistern toilets. The water there, as Monroe pointed out, you could go back there and drink if you could stomach it. So that's the flush water, and then there's all that water in the household. I'm just going to go forward in the interest of time. Okay, so roughly, and these are rough numbers for Westerners, about 50 kilograms of wet fecal material, 500 liters of urine. We mix that with about 20,000 liters of flush water, and then another 120,000 of what I call gray water, all those other uses for cooking and washing. And so that's what leaves our houses usually into sewers. Okay, so in terms of components of wastewater systems, these are different sort of categories. You have a user interface with respect to excreta. In some cases, well, you always have some collection. In some cases, you have storage and or treatment on site. But in a lot of our urban, suburban areas, we go right from user interfaces through some local collection into conveyance. So this would be like sewers, for example. There can be some centralized treatment then, and then ultimately you either use the water that you recover from it or you dispose of it out into the environment. So under each of these, right, there are lots of different technologies that exist. And all I've done here is just highlight our typical ones in the US. We use a flush toilet. If we have any on-site storage or treatment, it's usually a septic tank. We use conventional gravity-fed sewers, although there is a lot of pumping that goes in to keep the water moving, especially on sort of horizontal sewer mains. We tend to involve an activated sludge treatment process, and then we have surface disposal, or in the case of Ithaca, I think you heard last week, it goes into Cayuga Lake. But there are many different options, and again, I'll go over just a couple of the other options that are on here. So what are the things that wind up then in this really mixed bag of wastewater that we're concerned with, right? Why can't we just dump it out into our yards or into the local creek? Well, because of these varied things. So we have suspended solids, biodegradable organics, pathogens and or parasites, nutrients, priority pollutants, so particular chemicals that are of concern in the environment, refractory or non-degradable organics, potentially heavy metals, and other sort of dissolved inorganics. So these are all things that we're concerned with to varying degrees in the wastewater that we flush down the toilet. Okay, so by and large, the sort of decentralized system that we use here in the US, I have it in my home, right? Many people who are sort of in rural or remote areas, although there are people even in New York City and the outer boroughs that still have septic tanks in their yards, right? And the idea here is you have the collection pipes from the home going into really just an underground tank. It often has sort of 2 little chambers, and it just gives it time to settle, right? So you get the solids and the sludge sort of building up in the bottom. You have floatables, like any oils or greases, or things that are lighter than water, building up on the top. And the water, though, is making its way through out into a leach field, so a series of pipes. So you have to have enough land in order you're essentially you're using the natural environment, the subsurface, to do the treatment of the water that comes off of there. So that's a sort of typical septic tank. But for any of the sort of centralized systems, this is a typical centralized wastewater treatment plant in the U.S. And I think Brian had a few of these sorts of these little guys here were on there. I think he had these 3. I think these 3 were there. All right, so we have raw sewage coming in again in our sewer mains. There's an initial step to remove a lot of the really heavy rocks and grit and things like that. And then you have this influent pump that actually pumps all the water up so that it can then flow down the plant by gravity from there. So as Brian pointed out, we first have a clarifier, so the water slows down in here. It's usually about 2 to 3 hours, or at least in the Ithaca plant, it's 2 to 3 hours here. And that allows some of the sort of organic solids to settle on out. Right, so there's these streams that go down that are called sludge, so that's pretty heavy in these solids. The water, the clarified water, then goes into these aeration basins, sometimes called activated sludge tanks. And this is where aerobic bacteria are going to town on it. So essentially, the main thing that's happening in here is all those organic material that's coming into the wastewater is getting converted to CO2, right, by aerobic organisms. Now, this is what would happen if you dumped your raw sewage into the environment. This would happen, right? But you would have major anoxia all over the place. And so the idea here is you have lots of bacteria in here. You bubble a lot of air in because they need oxygen. And they consume it really fast. So you're really just activating them, right? And you're getting them to degrade the organics rapidly. Right? Yeah.
So that step, what do they do in the wintertime? Do they have to just slow the whole process down, or so it can't be as efficient in the cold temperatures, is it?
You'd be amazed how much thermal energy there is coming in the wastewater. And actually, I'll touch on it later.
Okay.
There's an unappreciated amount of thermal energy. If you think about all the hot water we send down, or at least house water. So this stays pretty warm, and if you go down to the wastewater treatment plant, actually in the middle of the winter, there's like steam often rising out of the activated sludge tanks. Right, so here you're getting conversion, you're getting a lot of your organics converted to carbon dioxide. And then you have to, those bacteria, you don't want to wash those away for two reasons. One, you can't release them out into the environment, and number two, you actually want to keep them in your system because you recycle some of them to keep their density really high in there. So you have another clarifier, and you have a sludge coming down off of that, and your water flows from there. And in a sort of a typical plant where there's not tertiary treatment needed for like extra phosphorus or nitrogen removal, you'll have disinfection here. So this is a chlorine contact tank, so it just gives it a certain amount of time with chlorine in order to disinfect before various research. And this is from a plant in the Bay Area of California, so it has a couple different places, a golf course and out into the bay where it goes. Okay, so now these sludges, right, are actually, you can't just get rid of those as well. And so there's I'll just point out a couple things. There's this return sludge, again, some of the bacteria, just to keep the densities here really high, you do return some of that. But you still have an excess being produced. So these sludge lines, if you'll notice, they come together into this other chamber here called the digester. And instead of this being an aerobic environment, this is a very strictly anaerobic environment. And the idea here is that the remaining organics, or the bodies of all of these bacteria that have been grown, or these particulate organic material that's coming off the primary, gets converted to what's called biogas, which is a mixture of carbon dioxide and methane, right? Usually on the order of 70% methane, so very high methane content. And an important thing to notice, this dotted line here, that methane is not always used, but it can be used to power the plant. Right? You can have a generator on plant that burns that biogas. You still wind up with some undigestible solids from there, and those have to be landfilled or reused. But it's a small fraction of what comes in. And for the Ithaca area wastewater treatment plant, again, their range is usually 6 to 8 million gallons a day of raw wastewater that they're treating. They do tertiary treatment for phosphorus because whether it's an appropriate designation or not, I would love to sort of discuss, but the southern Cayuga Lake, the shelf, is considered an impaired water body for sediment and phosphorus, and so there's strict loading levels. So they have put in pretty recently a phosphorus recovery system.
All right, Paul, is there a second? So what did you tell us the last time, Brian, that it was that the water plant does 2.6 million gallons a day, but they're putting out 60.
Yeah, they take from different systems. There's like 3 different water distribution plants that funnel into the.
Okay, thank you.
Yeah. And they do use the biogas, and they've made some recent upgrades, in fact, to their digesters, and they power up to now 60% of the energy that they need.
Can you comment on the spatial correlation between golf courses and wastewater treatment plants?
It's got to be pretty close. Right? Water is heavy, and water takes a lot of energy to move it anywhere. So if we don't have a convenient local location, I don't know why we don't. Actually, the golf course is very close by, actually, in Ithaca.
Excellent.
I don't think that I don't know if they've ever discussed that. They may not have the same water stress or water problem that they have, say, out west. Okay, so but some of the challenges to this current infrastructure, it works, you know, and there's a rare exception. I don't know if you read in the papers last month, there was some unknown, I don't know if they've determined, major shock load of something toxic, and it wound up killing, or really, you know, inhibiting those bacteria in the activated sludge tank. So the plant was operating suboptimally. But 99.9% of the time, it operates just fine. However, there's a very high energy usage, the pumps and the aerators being the two big ones. I think Brian pointed this out last week. There is really a pretty big, heavy price tag in terms of doing repairs or upgrades to our aging infrastructure. Greenhouse gas emissions, both tied to energy consumption, fossil fuel burning for the pumps and aerators, but also there's potential for both nitrogen and carbon greenhouse gases to be emitted from these wastewater treatment plants. As I'll mention in a little bit, there's lost opportunity for energy and nutrient recovery as well. In many communities, not in Ithaca, there's also combined sewer and stormwater, and so with potential climate change effects of climate change on rainfall events and severity, you could wind up having a lot more stress on these systems. And with respect to septics, they tend to be sort of one of these out of sight, out of mind technologies. They could be totally non-operational as long as they don't back up into your house. You could go on for years like that, not sort of realizing that there's not sufficient treatment. Okay, there's some sort of basic modifications, well, some basic, some not so basic, that could be made to these existing systems. Simple, you know, thinking about energy efficiency in these centralized plants, really having the most efficient pumps, right, if those are your major energy draws, targeting them as you do your upgrades. Capturing more of the biogas for use. So many plants just flare this off, even if they use the technology. They don't use the energy, they just burn it, so they release it as CO2 off of their digesters. Recouping the heat contained in wastewater, again, there's a decent amount of energy content, heat energy content. Mm-hmm.
I'm guessing for the digesters, it's the initial investment that is keeping a lot of plants from doing that.
Probably, you mean for the generator, for being able to...
Yeah, well, yeah, just the cost of that digester, yeah. Do you have any...
But even people that have digesters, they don't all use the biogas that gets produced. Because of the additional cost of getting the conversion equipment.
Do you have any sense of like how fast that might pay back if they do use that to?
I don't know. I don't know those numbers off the top of my head, but I would be willing to bet it's within that magic 3-year time frame. This is such a energy. Do you know?
No, but I know Johnson Controls for the Ithaca wastewater treatment plant. Johnson Controls has an energy performance contract with them. And I think the city and the town are each putting in $1 million, but the renovations I think are close to $8 million. And Johnson Control is fronting the rest of that money because they're going to make it back in the savings in energy that's going to occur.
Huh. Okay. Okay.
So they must feel like they can make a fair amount of money by making that plant more energy efficient.
Right.
And I was just going to add that I think on the flaring problem, I think I worked in agricultural digester setups, and we had a problem of getting like very small units. We couldn't get a generator that was small enough that would fit, and so I imagine that maybe the plants that have digester capabilities set up in their
larger
just can't buy the unit that's small enough.
Okay, that could be.
Which is another thing too, because a lot of the treatment plants that have been built in the last 20 years are quite small. And I know some of them, like down in the Binghamton area, the woman who ran the Binghamton wastewater plant was also did some of the management. She consulted on the smaller ones, and she was saying for some of the small plants, the heat in the winter is a problem because they're just not getting enough.
Huh? From their wastewater.
From their wastewater, yeah, to maintain the heat in the plant. So which is interesting when you get into these scale issues. So.
Right. Yeah.
And that may also be a problem with the digesters too. They're just not big enough to justify.
Right. Good. And then, you know, getting into sort of a bit more sort of real modifications, changing to more compact processes that require less concrete, less pumping. So there's, coming out of Europe, there's a lot of research and some full-scale plants with these high-rate aerobic granular sludges. So rather than having to settle the bacteria, recycle and pump them around, you actually have the bacteria are in these granules, and you flow your waste up through it, and they just sort of stay there, and they so they stay in the tank, and the water percolates through them. So you don't have to. You can have a smaller unit, and you can pump less recycle. Finding ways to recover N and P in usable form, so nitrogen and phosphorus, from a wastewater perspective, they're things we need to be getting out of the water, because if we release them out into Cayuga Lake, you can have algal blooms, right? So even if you get rid of all the organics, if you have these limiting nutrients that you release, you can wind up causing environmental damage. But as I'll show you in a second, those can be really looked at as recoverable. But challenges, because again, this is a very dilute waste stream. Even if you can avoid treating the nitrogen and phosphorus, you have a very dilute stream here. And then for the distributed systems like septics, there's options for modified septics for trying to recover the biogas. And we don't try to capture it. So and there's studies done with greenhouse gases emitting off of septic tanks. Another case of out of sight, out of mind. Yeah?
I'm just wondering, because of different backgrounds in the audience, if you could like throw up chomps and say what that means as like, why do we care about N and P? Like, you
sure.
know what I mean? Like, because I feel like you could do that fairly fast.
And this is sort of in the order. These are elements, so carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, sort of in the order in which their importance or their abundance in biological systems, right, in need. So, you know, carbon, hydrogen, oxygen, pretty straightforward, but definitely nitrogen and phosphorus are also macronutrients needed for proteins and nucleic acids and energy currency like ATP in the cell, and then sulfur in some of the proteins. So you wind up getting limiting nutrients. So in terms of releasing nitrogen and phosphorus, right, these are certainly further down on the list than carbon, but algae, for example, in Cayuga Lake, they can get an unlimited supply of these things from water, and the carbon dioxide from the atmosphere dissolved in that water. But these wind up limiting their growth usually. So you wind up, that's what then eventually causes blooms. Is that what you started talking about?
Yep. Yeah.
All right.
Sorry.
That's okay. And the idea of treating gray water and black water separately. Okay, I am going to run out of time, I think. So this is a review actually from a couple years ago by Perry McCarty, one of the godfathers of environmental engineering. And he kind of has, it's hard to make out the fine print here, but these are sort of constituents that are typically thought of as problems in wastewater. And their typical concentrations. And then he's trying to have an energy perspective in terms of looking at wastewater again as a resource. And this is in kilowatts per cubic meter, so kilowatts per 1,000 meters. And then there's three categories. So maximum potential from organic oxidation associated with these organic compounds, right? So totaling just shy of 2 kilowatt hours per cubic meter. And this is sort of just looking, you know, so thinking of, say, the methane that gets produced, when you burn that, the energy that can be recouped. Or even just the solids themselves, if they could be dehydrated and burned, the energy that could be recouped from that. And then there's the required energy to produce fertilizing elements. So this is where the nitrogen and phosphorus, you really start looking at a little bit differently. In particular for nitrogen, ammonia is extremely expensive to make for a conventional fertilizer. Taking atmospheric nitrogen and making ammonia out of it is a very energy intensive process. So that nitrogen sort of has this embedded energy as well. Phosphorus has much lower in terms of the amounts that are in wastewater. So to combine, they have about 0.8 kilowatt hours per cubic meter embedded in them if you can recover them. And then there's this thermal heat available for potential heat pump extraction. So doing some heat exchanging there. And that's actually the biggest of them, but it's only good for heat, really. So again, so that's about 7 kilowatt hours. So this is sort of rethinking in terms of wastewater as a resource. And how might you change your plant in order to extract those resources or make the most of them. But then there are major changes that are possible as well if we rethink this habit of taking all of that fresh potable water, mixing a small amount of excreta into it, and treating it all in one big centralized, pumping it somewhere, treating it all in one centralized place. These are pretty straightforward. So it's starting to sort of think about water, sanitation, and agriculture not as 3 separate challenges, but like trying to think about integrated systems for dealing with all of 3 of them at once.
Could you just back up one step? Because to me, I'm always bugged by the fact that we put industrial, like it's bad enough we use all that water to take out excreta, but you add, industrial waste and suddenly it's totally toxified. So is there any, and then the sludge is no good or it's toxic.
Right. So the industrial facilities need to do their own treatment.
Now they do? They're required to?
Yeah.
Oh, I didn't realize that. All of them?
Yep.
Oh, cool.
My impression was that they have pretty strict standards. If they utilize water, they can't just release chemicals back into a domestic sewer. But this is pretty much a domestic.
Great.
Now, that being said, anybody at Cornell who doesn't know any better or, could be in a laboratory with something really toxic and send it down the sink. And so there's accidents that happen. But by and large, yeah, industrial waste doesn't come into these systems. Okay, so sort of this idea, you have a watershed, you're drawing out your water, you're treating it, you're sending it to your community, right? And then after it's used, you're sort of treating it and then replenishing or reusing, some combination of the 2. But then the other loop that's shown here is this sort of nutrient loop. So we wind up, again, because in our excreta, we naturally have these nutrients, and thinking about those loops and trying to keep them more local. Okay, keep those nutrients in circulation. Skip this, but at the household level, you can do this, not just at the community level. And so it makes us sort of step back and start thinking about the waste products separately in the different terminologies here. So we have excreta, so that's urine and feces together. That's the term we use for that. Black water is that urine, feces, and flesh water. Yellow water is if you can separate out the urine. It's considered yellow water. Gray water, which has already been brought up, is wastewater from the kitchen, the bath, and the shower. And then fecal sludge refers to the solids, the sort of wet solids that accumulate in certain sanitary systems. Okay. And a sanitation system has to handle them all. Okay, so looking a bit at some of the characteristics of waste products separately. All right, so the main 3 are going to be gray water, urine, and feces. Now, we've already gone over the fact that in terms of volume per capita per year, gray water is just dwarfs the urine and the feces. In terms of nutrients, however, in particular nitrogen, urine has the vast majority of the nitrogen in it. Okay, it has a very high concentration relative to either feces or gray water. Right, so urine really is where the nitrogen is at. Phosphorus, again, the majority is in urine. There's a little bit more represented in feces. And then potassium, again. So urine has a lot of nutritive value in it in terms of nitrogen, phosphorus, and potassium. In terms of the organic material, urine does not have very much. Gray water and feces sort of split the majority there. Okay. And then in terms of fecal coliforms, urine, if you're a healthy person and you're not cross-contaminating, there's actually no pathogens in your urine. The majority of the pathogens, or the fecal coliforms, I should say, the indicator organisms, are in the fecal material. But depending upon the gray water, you can still, you're washing things, or it sort of sits and bacteria grow in your food waste. You can still have a good amount. So we can treat these or think about them differently as long as we don't mix them together. So those are the big things. And then I'm just going to sort of jump in these, again, the same 3 categories. For value, Gray water has reuse potential for irrigation or non-potable domestic use. Urine nutrients is the big story there in urine. And then feces, there are some nutrients. There's a good soil conditioner, but fewer nutrients. I really wouldn't call it little. Okay, so I grabbed this because I saw you wanted a little bit of gray water while I was listening to Monroe. There are a number of, and this website here, I would definitely recommend that all of these technologies, they have great information on all of them. So like this page, you can then click. I'll be glad to tell you exactly. It's not right at this page, but there's some sub-pages. But there's a lot of different sort of options, some of them pretty similar to what we already do, like leach fields from a septic system, but it's just not as much stress on the septic. Okay. I'm going to run out of time, so I'm going to move a little quick. And I'm going to tell you then about one technology that I'm kind of excited about, especially as I start to think about sustainable sanitation. But except for culturally, there's no reason it couldn't work as we really rethink our systems here. So that's the urine diverting dry toilet down here. I'll show you on the next page. So this is a side view, and this is a sort of a front view. So you have two different chambers, right, or two different alternating toilets, really. And the toilet in operation, there's actually, the interface has a urine compartment and a fecal compartment. And so they actually lead to two different things. So there's a little can here of urine, and then there's a collection basin here that collects the feces. You do wind up adding some ash or sand or lime here. So the idea is to keep moisture out of here and get it dried out, to dehydrate it. So you're not even trying to compost it. You're not trying to anaerobically degrade it and get methane. You're actually trying to sort of preserve it and make it sanitary by dehydration. Okay, so you wind up having these two streams. And then once these are full, you cap it, you use the other one. And then these sit, depending on, the urine can be as little as 3 months. The feces, usually you let it go for a year where it just sort of sits there, and then you have usable products for agricultural usage. Okay, there's definitely some advantages, definitely some disadvantages, and culturally, it's a big challenge for us to think about not having flush toilets. With respect to the urine, there's sort of two general options. One is direct application, so after some storage time. But you can also precipitate, if you add some magnesium salts, you can precipitate out this struvite mineral, which contains both nitrogen and phosphorus in it. And so you get this sort of powdery material that can be used. Okay, so those are just a couple of examples of really different technologies that exist that I'm excited about and I'm going to start doing some research on. And so I'll sort of wrap it up and summarize that in the US our tradition is to mix all these things together into a dilute waste stream, and then we tend to treat it centrally. While our systems can treat it, right, thanks to physical, chemical, biological processes, there's real costs associated with it, both capital costs for the infrastructure, energy costs, and wasted chances at resource recovery. But there are several technologies and systems that exist that can handle different waste streams and water streams differently as to maximize recovery potential without, of course, sacrificing sanitation, good sanitation. And that's it. That's what I've got. Yeah, Rebecca.
I love dry composting toilets, so you brought some new idea for me, but why do you see that you're separating composting toilets a better alternative than the dry composting, where you literally make kind of like soil, healthy soil?
So are you talking about like composting toilets?
The dry composting ones that they use, like in some students we had worked on them in Mexico, so all the material goes to the back of the system, and then it decomposes. You have a lot. You don't add lime or ash. You tend to add like sawdust or straw and stuff. Right.
My experience, and I'd love to talk to you more about it, because that's the other option that I think does make sense. There's a lot more individual interaction with compost, and there's moisture and oxygen conditions that have to be just right. Right. And nitrogen to carbon ratios that have to be just right. And so you have to do a bit more management and monitoring. Cool. Than you might have to here. So
Eco Village has 3 of the dry composting systems, and one I don't think worked, but the 2 others are. I'll have to look, I'd like to talk to you more about that other
Yeah.
alternative, that's cool.
So I just wanted to say we can stay and talk more if you
Yep.
guys are willing.
Yep.
But if you need to go for whatever reason, then you can do so. Next week we'll have Todd Walter, who's from biological and environmental engineering. I don't really know what he's going to be talking about yet, but I imagine it's going to be something about hydrology, perhaps green infrastructure. I made up the title of this talk, so hopefully he'll follow that.